Welcome to this explainer. Today we're diving straight into an incredibly fascinating topic, an introduction to Francesco Cester's book, Newton and Relativity. For over a century now, we've kind of just accepted that the brilliant, grounded mechanics of Isaac Newton and the totally mind-bending relativity of Albert Einstein are, well, separated by this massive, uncrossable conceptual gap. But what if they aren't? Today we're exploring some absolutely groundbreaking insights from Cester's work. He actually proposes a bridge between the two, and let me tell you, it is a wild ride. So let's kick things off with a question. Do we really, truly have to just abandon our classical intuition to grasp relativity? Look, if you've ever sat through a physics class or maybe read a popular science article and just walked away feeling completely confused by the whole relativity thing, let me just validate you right now, you are absolutely not alone. It is notoriously difficult to wrap your head around. But what if the way we've been taught to understand the universe at high speeds is actually missing a crucial, totally classical puzzle piece? Okay, let's dive into this. Section 1, the historical physics conflict. To really get why this proposed solution is such a big deal, we have to understand the crisis that started it all. Let's travel back to the late 19th century. Physics was essentially going through a colossal clash. On one hand, you've got classical mechanics, right? Built on the super solid, absolute foundation of Sir Isaac Newton. But on the other hand, this bold new framework was bubbling up. Let's trace how fast this happened. First, Scottish physicist James Clerk Maxwell brilliantly unifies electricity and magnetism with his famous four differential equations. Total triumph. Except for one glaring issue. Maxwell's equations completely clashed with Galileo's transformations, which were literally the bedrock of classical kinematics. Then, in 1886, along comes Michelson's interferometer experiment. This proved that the speed of light is constant regardless of the observer's frame of reference, which, again, directly contradicted classical mechanics. Finally, in 1905, Albert Einstein steps into the ring to resolve the whole mess. Which brings us to Section 2, Einstein's radical solution. Einstein, building on the work of Dutch physicist Hendrik Lorentz, basically solved the contradiction mathematically. They tweaked mechanics so it fit perfectly with Maxwell's equations and that tricky constant speed of light. But man, this mathematical victory, it came at a huge, huge cost to human intuition. To make the math actually work out, Einstein's special relativity introduced some seriously mind-bending consequences. Get this. Events that look simultaneous to you might actually not be simultaneous for someone moving past you. Clocks in motion, they physically slow down. That's time dilation. Objects literally shorten in the direction they're moving. And the ultimate rule, nothing can exceed the speed limit of light. Just like that, the absolute space and absolute time that Newton so firmly believed in were completely tossed out the window. Moving on to Section 3, the problem of skepticism. Now, because these new rules go against basically everything we experience in our normal day-to-day lives, being skeptical is completely natural. Honestly, if you find time dilation and length contraction a bit hard to swallow, you're reacting exactly the way a rational, observant person should. The author, Francesco Cester, relates to this perfectly. In his preface, he writes, "Those who are reluctant to accept these assumptions tend, more or less unconsciously, to take a skeptical attitude toward the theory itself." Cester himself lived with that exact skepticism for a long, long time. And you know what? It was that very feeling that drove him to look for a different path. He wanted an intuitively accessible way into the theory of relativity, one that doesn't just demand we blindly accept paradoxes. So, what does he propose? Section 4, a new classical approach. What if we didn't actually need all those abstract transformations to understand the universe? What if there's a new classical approach just hiding in plain sight? Well, the initial spark for Cester's new approach actually came from a scientific paper by a physicist named Fritz Röhrlich. Röhrlich published a paper that proved something completely astonishing. He showed that Einstein's most famous equation, E equals mc squared, the equivalence of mass and energy, can actually be derived entirely from the laws of classical physics. He did it using the Doppler effect for electromagnetic waves, meaning it doesn't even presuppose relativistic mechanics in the first place. Crazy, right? Let's contrast these two approaches to see exactly how Cester's new methodology shakes things up. On side A, we have the established method, the one we've all been using for a century. You start with the postulate that light speed is constant, you use Lorentz transformations, and you throw out absolute space. Sure, it's mathematically sound, but it's incredibly hard to intuitively grasp. Now look at side B, Cester's new methodology. Here, we actually replace those unintuitive postulates with classical mechanics. We start right at the foundation, Newton's second law and that classically derived mass-energy equivalence. And that takes us to Section 5,
reimagining Newton's second law.
Now, what's really interesting here is the secret ingredient making this whole new approach possible. It requires us to look at Newton's famous second law of motion a little bit differently than, say, your high school physics teacher might have taught it. Usually, scientists restrict Newton's second law to constant masses and low speeds. But if you look at the strict definition, the time derivative of momentum, the law actually consists of two parts, two distinct terms. The first term describes the change in speed. Okay, we all know that one. But there's a second, widely ignored term. This one accounts for a change in the inertia, or the variable mass of the body that the force is acting on. By bringing the second term off the bench and putting it to work, Cester shows that Newton's second law remains perfectly valid even at extremely high speeds where mass actually begins to vary.
Which naturally leads us to Section 6, the logical extension.
Cester structures the mathematical proofs in his book to demonstrate a complete framework, and it unfolds in 3 really elegant steps. Step 1 examines the true scope of that second law we just talked about, providing alternative, purely classical proofs for E equals mc squared. Then, in Step 2, he uses that expanded second law to derive exactly how mass depends on velocity, effectively extending the calculation of kinetic energy to speeds near the speed of light. And finally, Step 3. This is the big one. He uses pure classical conservation laws, specifically energy and momentum, to theoretically confirm the constancy of the speed of light in a vacuum. He actually proves it. He doesn't just ask us to assume it as a starting postulate, like we've been doing for 100 years. By properly applying that often ignored second term of Newton's second law, Cester arrives at 3 massive, game-changing conclusions. Number 1, E equals mc squared is a classically derivable principle. Number 2, the constancy of the speed of light is a provable physical law, not just some postulate you have to accept blindly. And number 3, special relativity is actually a logical extension of Newtonian mechanics. Basically, Newton's laws form a much broader, far more powerful physical basis than the scientific consensus has assumed. It's a total paradigm shift. Which leaves us with this final, thrilling thought to ponder. If something as notoriously paradoxical as relativity is actually just a logical, intuitive extension of classical Newtonian mechanics, what other paradoxes in modern physics might be hiding simple, intuitive, classical solutions, just waiting for us to uncover them? It really makes you want to rethink everything you know about how the universe works, doesn't it? Thank you so much for joining this explainer. Keep asking those big questions, and as always, stay curious.